Okay, where are we at? We're at
45.
45. I'm kind of thinking maybe we should get started because
Yeah.
it's already 3 minutes
Yeah, it's
after.
fine. Yeah,
And
the first 5 minutes will be about this photon collider questions other people
okay, great.
the student
Yeah.
ask. So for those who arrive late, they just missed this part, which is perfectly fine. Yeah.
Okay,
Okay.
great.
Yeah.
All right, so yeah, maybe please go ahead.
Okay. Good afternoon, everybody. Glad to see you. Can't really see you guys, but I imagine you guys are there sitting there carefully with a coffee. Okay. So yesterday a student asked a question about photon colliders. In my original lecture notes, I did not prepare for it since we haven't really talked about that for quite some years. I mean, nowadays when they talk about future colliders, it's always E plus E minus or PP. So, you know, but but there was a lot of discussion about the photon colliders earlier. I think that was about 20 years ago in the Snowmass 2001. And so I dig it out a little bit more so that, you know, about what photon collider is good for. Okay, because if you think photon collider with the photons, I mean, it's not like, you know, the E plus E minus in the standard model, you know, photon doesn't interact with photons, or directly speaking, but on the other hand, you can go through some T-channel process. So I dig out a little bit more details about what photon collider is really good for, and to my surprising, they actually have quite large cross sections for certain things over there. So I'll just use the first 3 minutes, kind of add a little more things about the photon colliders over here, since nowadays we don't talk about that anymore. Okay, so the photon colliders people nowadays were talking about are the real photon colliders. The one that Tom mentioned the last time, you know, about any E plus E minus is a photon that's like a virtual photon coming out. But this one is really a real photon colliders. And it kind of come into picture when people start talking about linear lepton colliders, you know, because when you want to go to higher center mass energy, circular machine no longer works because of the synchrotron radiation. So you want to have a linear. But once you have energetic kind of electron beams in the linear colliders, and you can actually, let me use this one. You can actually shoot a very high intensity laser beams, a low energy laser beams. Then they would interact with the electrons kind of just through the usual Compton scatterings. And this is like, and then they will have energetic photon coming out, which are those guys, which carry most of the electron energies. And then you have the other photon beam coming from the other side. So those are really the real photon emission over there. And if you design your technology well, the photon, as I said, will carry most of the incoming electron beam energy. And they wouldn't lose too much of the luminosity as well. So you really get two energetic photon beams collide with high luminosity, and then you see what coming out of it. So that was kind of the basic idea for the photon colliders. So what can it be used for? Actually, comparing to the E plus E minus collider at same center of mass energies, they can actually do pretty well, to my surprise. And then I think about it, it actually makes sense. Okay, so let me pick one of the E plus E minus one. Okay, so all the solid lines of the left part, the solid lines are for the photon-photon collider cross sections, and the dashed lines are the E plus E minus one. So let me pick this one over here. E plus E minus goes to WW. Okay, so in the standard model, you basically go through a photon or Z S channel, then goes to, you know, so it's those kind of processes over here as channel processes. Okay, but photon colliders, what do? The W carry charge, so you actually have a photon, and then it's a T-channel process. You have W over here, okay, and then exchange a W over here. So the nice thing about the T-channel process is that the cross sections actually goes as a log of S. It actually goes up a little bit with the center of mass energy. So the more center of mass energy you have, you actually would have more cross sections over there. But the S channel ones, the cross sections actually goes as 1 over S. So the more center of mass energy you go, the cross section actually goes down. So the gamma goes to WW actually have the cross section almost 2 order magnitude, then the E plus E minus goes to WW over there. Okay, so that's kind of one thing that the photon colliders is good at. You can actually study all those the W interactions. For example, you can see if there's any deviation from the standard model predictions and all those sort of stuff. Okay, so and you can also, for example, look at the TT bar And they would wear the standard model TT bar. Yes, the standard model, not the standard model, E plus E minus TT bar is given by this dashed line over here. So again, you can see that the photon colliders has more cross sections. So actually for quite some processes, the gamma colliders actually has more cross section than the E plus E minus ones. A bigger cross section is of course better, given that they have more events coming out. So you can use the gamma collider to study, anomalous W couplings, Z couplings, TT bar couplings, the TT coupling, and the top couplings and things like that. So that was one thing. And another thing that's good at is actually you look at the right plot, which gives the corresponding Higgs projections. Okay, so the gamma directly goes to Higgs. For example, you have gamma triangle diagram goes to Higgs. Okay, comparing to the E plus E minus, oops, where does it go? Okay, here. E plus E minus will be like this. E plus E minus goes to Z, then it's a Z H. Okay, so first of all, it has more cross sections. That's good, but that's not just only it. The second thing is those are the two, oops, those are the two gammas directly go to a Higgs. Okay, so say if I have a 500 GeV gamma colliders, I can basically pretty much produce a 500 GeV Higgs over here. Unlike here, it's the ZH associated productions. So once the Z boson takes away certain center of mass energy over there, so you can mostly produce Higgs, say up to 400 GeV or something like that. So you actually have more center of mass energies to be able to approach heavier Higgs, on top of that has bigger cross sections over there, okay? And also you can use a polarization of the gamma to study, say the CP properties of the Higgs, whether it's CP even or odd, or it's a mixture and all those sort of stuff over there, okay? So the gamma colliders compared to the E plus E minus does have the advantage to study certain processes. So that was to answer one of the questions that one student mentioned about gamma colliders. Since I'm not going to talk too much about gamma colliders, I thought it's worthwhile just spend 5 minutes on that in the beginning. Okay.
There's a question in the chat.
Okay.
About the gamma to TT bar.
Okay. Take the gamma TT bar, for example, to agree with TT. Oh, it's a phase space. Yeah. Yes, because for gamma, let me use this as so it's so gamma for the TT bar. The naive thing I can think of is just this one, okay, with a TT bar over here. And if it's E plus E minus, yes, in principle you could go to the T. Let me see, is that the one you're talking about, the E plus E minus? Let me see, how is the TT coming out? Can probably goes to, how do I get that cross sections over there? I could get, it will go through a Z or something, then it could go to W nu, for example. That would have a Z or gamma. So I mean, so this is the two-body final states. Doesn't matter. It's a two-body. One is a two-body final state versus one is being a four-body final state over there. So you have a phase space suppression when they have more particles in the final state. So and also you would have more couplings, so you also have more suppress because all those are electric couplings over there. So you have more suppression over here. Let me see. Do they have a E plus E minus goes to nu TT? With this one over
I think it's going to be really small.
I didn't see it.
No, I mean with the gamma collider, I think the confusion is this is really genuinely a beam of photons. Like the conversion of the electrons into the photons happens like tens of centimeters away from the interaction region by this super intense laser pulse, right? Right.
Yeah. So it's a real photon. In that sense, it's a real photon collision.
The photons are on-shell photons.
Right. It's an on-shell photon. Correct. Yeah. So it's unlike the usual Bremsstrahlung of a photon coming out, and those are kind of virtual photons. Yeah. So this one, the people talking about are really the real photon collisions over there. Okay. How do we make sure the most of electron? So that's to do, okay, so that I'm definitely not an expert, okay? That's to do with accelerator physics over there. And the basic idea is you shoot very intensive laser beams over here, low energy laser beam, but very intense. And then hit the electrons, it's a complex scatterings, and then they can, with whatever technology they're using, they can convert most of the energies into the photons, and also be able to produce a lot of and also without losing up too much luminosity as well. Okay. And, okay. And, okay, there's Yama also post something about effective photon approximation. That wasn't really for this. I would say for the usual ones, that especially the one that Tom mentioned yesterday, yes, it's effective photon approximation. But this particular one, I'm not 100% sure, because this is really a real photon coming out. Unlike I just have E plus E minus and just radiate out a virtual photon over there. There, yes, people use effective photon approximation. Yeah. Okay. Let's get back to Lepton colliders, guys. Okay. Okay, so now let's start today's lectures. Okay, so last time we end up with a comparison between lepton colliders and the proton colliders. So today, let's just talk a little bit more details about what each of those colliders are good and bad at, and what's the typical techniques or the one we use to analyze things in those colliders over here. So I give a list of a bunch of colliders that we have had always, or is planning, or at least the people are designing. So the top ones over here, LAP SLC and the LAP 2s are the ones that we had. You know, they have center mass energy somewhere between MZ and 210 over there, which did a lot of, you know, ZPO precision measurement, which helps to establish the standard models. And then those are the ones that people are planning. So for the CEPC, I should also add, it's the same as FCCEE. The European version over here. So the ILC, International Linear Collider, it's a linear collider beam. So the good thing is it's a linear collider, so you can really get to center mass energy, you know, higher, 500 GeV or higher. And then the FCCE and the CEPC, they are at lower center mass energy because they're really designed for a Higgs factory. After people know that the Higgs mass is actually 125 GeV. So by design a 250 GeV machine, you actually peak the cross section, so you can produce like 1 million Higgs. Then just like lab being Z factories, do all the Z precision measurements. Here you can really make a Higgs factory and do all those Higgs precision measurements, you know, really measure the coupling, like the ZZH coupling down to sub% level, like 0.1% or 0.2%. So that really helps to basically pin down what kind of Higgs are you seeing. Is this really the standard model Higgs or beyond the standard model Higgs or things like that. And then CERN also have the plan to do the click. You can see the amazing center of mass energy over there, 3 to 5 TeV. Okay, so that's again a linear machine, use different technologies, really boost up to, so even though it's a E plus E minus machine, it's really get to the energy frontiers of 3 to 5 TeV over here. So that was for the future. So what's the advantage of a lepton collider? First thing first, it's an E plus E minus system. What's so good about it? You add up all the charge, total charge is equal to 0. You add up all the lepton numbers, the total lepton number is equals to 0. So it's a perfectly nicely kind of neutral system over there, which is that it will be really be suitable to create new particles, and most of the time in pair. Because, you know, anything that carries a charge, anything carry, you know, either electromagnetic charge or the SU2 interactions, then just the E plus E minus goes to S channel, then it produces some in pairs, you know. So it's really good to create those new particles, as long as it's within the energy reach, because energy is always the thing about this E plus E minus collider. So even though you can, you know, mostly pair produce some, but you have to within its energy reach over there. So if the particle gets too heavy, then sorry, too bad, you know, you just can't produce them. The second thing is E plus E minus, you really have a symmetric beam such that the center of mass energy frame is basically equals to the lab frame. And yesterday we talked about that. The square root of S, which is the center of mass energy, which you can basically maximally use that to create any new particles, as long as it's within its kinematics threshold over there. Okay, and then later on when I talk about the hadron colliders, you will see the difference. Even though the proton-proton is also a symmetric beam, but because it's actually parton inside it that's interacting, the center mass frame is actually not the lab frame over there, and some of the energy kind of getting wasted. Okay, and the third thing is, again, because E plus E minus are the fundamental particles, you have a well understood beam properties, which is, you know, you can completely reconstruct the whole things. You know, the whole kinematics is completely known. I mean, all the energy momentum get conserved, you know, in all the three directions, and you also exactly know what the incoming beam momentum is. So you can completely reconstruct the kinematics. Again, that's different from the hadron colliders. And the number fourth thing, which actually makes the E plus E minus machine a very nice precision machines, is its low background. Because E plus E minus, they don't have strong interaction. They only have SU2 and the U1 over here. So the cross sections you're mostly looking at is about 10 peak bonds. Okay, or if I write in terms of the nanobonds, 0.01 nanobonds over here. So even if I have a luminosity, say 10 to the 34, which is kind of designed luminosities for most of the future machines over there, that will lead to the number of events like 0.1 hertz events. So you have, you know, one event every 10 seconds over there. So that's no problem for the detectors to actually record them. Okay, this again, it's very, very different from the hadron colliders. So in the Lepton colliders, you basically don't need something called a trigger. Like anything happens, most of the time nothing happens. Anything happens, not most of the time, quite some time. Anything happens in your collider and in your machines, you can basically record them completely. Okay, so it's a very low background, and you can basically record any events, any interesting things over here. So that's a nice thing about the E plus E minus. And the last things, which pretty much only applies to linear colliders, since people do talking about the linear colliders as the E plus E minus that can possibly go to higher energies, you can actually do polarization of the beams. And as we'll also mention later on, to making use of the polarization, you can actually approach the chiral structures, chiral couplings of your model, of your particular model over here. Okay, so those are kind of good things about the E plus E minus. As long as it's within its energy reach, then you can pretty much, you know, study the events to death. You know, you can basically do all the measurements you have. So what's the disadvantage? As I actually already mentioned, one is energy. And the reason that it's so difficult is because of the synchrotron radiation. And radiation. And I has mentioned yesterday that delta E goes as 1 over R, E over ME to the fourth power. So because the electron mass goes in the bottom over here, you have way more synchrotron radiation for E plus E minus than for the PP colliders over here. Okay, so that's actually, do I have a question? Oh, it's still, sorry. Yeah, it's still about the photon. Let's leave photon for the moment. Okay, so you have tons of energy loss over here. So given radius size, you can, there's really a upper limit, a cutoff for the amount of energy you can reach for E plus E minus circular colliders over there. So that's why back in 2000 or 2001, for the snow mass we have, you can see people pretty much abandoned the idea of the E plus E minus circular collider at that time because Higgs hadn't been found. We don't really know what the next energy scale is. So if we want to have an E plus E minus machine, the E plus E minus machine better have higher center of mass energy. Then the choice you would have would be those linear colliders. You know, you basically, instead of regular circular machines over here where you keep circling electrons and have a lot of energy get radiated, so you're limited. So, but if you be able to accelerate E plus in E minus just linearly. And they can possibly, with new technology, you can possibly reach higher send-off mass energy, which is good. Okay, but on the other hand, there are challenges for those linear colliders. One is the reason people use circular machine is every time you circle around, you goes up your energy. So you can circulate many, many times and they can really boost up your energy. For the linear machine, you can't really do that, right? It's not like you go over there and make a U-turn. You just can't do that. You just have one shot to really accelerate things to higher energies within, you know, 30 kilometers or something. So technology-wise, it's very challenging. And also the luminosities for the linear colliders is also challenging. So again, it's because you don't have storage rings. You really need to accumulate all those E plus E minus over there, you know, have a focused beam. So it's also difficult to achieve high luminosities for the linear colliders over here. And even though you don't lose as much energies as the circular machines, you do have the beam strong, which is basically the Bremsstrahlung that you have for the beams over there, which would again affect the energy and the luminosity over here. So you need to carefully take that into account. Okay, so that's one disadvantage for the E plus E minus machine. You are limited by your energy basically. Okay, and then the second thing is, yes, so that one I kind of mentioned yesterday in comparison with the photon colliders, is you have the E plus E minus, and you mostly just goes to, you know, the photon and Z's or photon, virtual ones, and then goes to things over here. So the particles you're good to couple to so will be, you know, the spin one vectors bosons will be good if you do your partial wave analysis. But other than that, anything like spin zeros for the Higgs over there, or anything, you know, like spin 2, if you want to do a S channel production, just to singly produce those particles, it's actually going to be suppressed over there. Okay, so that actually, when you look at the photon colliders, it's actually better in terms you have more access to those, you know, S channel on-shell productions for those other spin particles over here. So that was kind of another things for the Lepton colliders. But given that Lepton collider is still a useful tool that we have, and it's the Higgs factories is the one that we're hoping to have in the future. Let's look a little more details about, you know, what kind of processes or the productions that you would have for the Lepton colliders. So the next topic is the particle productions. And
so Shufang,
yes. Mm-hmm.
I believe there's one question that we missed that was not about photon colliders.
Ah, okay.
The question was, why do people like to build lepton colliders with symmetric beams?
Okay, so symmetric beams is because you can maximally use the center mass energy to be able to reach new particles over there, because new particles typically heavy. And lepton colliders, as I said, it has advantages of the low background, the clean environment, so you can really do precision measurements. So you can do much better precision measurements at lepton colliders compared to the hadron collider that I'm going to talk about later. Okay, so if you look at the comparisons, usually people take lepton colliders as precision machines and the hadron colliders as energy frontier machines. You know, like you produce those new particles as at PP machines. So for example, the W and Z was actually at a PP bar machines over there. And then you build a lepton collider, say the lab, to really study the Z properties, to really do those precision measurement of the Z properties over there. Okay, so that's really, and if we are lucky enough, it will be good to have both, right? So you can really, you know, do both precision and energy reach either at the same time or consecutively, but yeah. Okay, so the particle productions, say I have oops. Okay, say I have E plus E minus goes to two particles, say A and B, okay, because usually they appear produced over there. And in the center mass frame. And if I just naively write down the cross sections for E plus E minus goes to AB over, say, the polar angles, cosine theta over there. And roughly it will be, and if we sum over all the azimuthal angle over there, assume it's unpolarized beam, then it will be something like this. Okay, so the beta over here is basically the momentum of the outgoing particles in the center of mass frame over there. It's basically one of those phase space effects over here. And the sum of the m square is basically the matrix element square. So that you can basically get it once you have a series. And you have the interactions over here. Okay, so that's roughly how it will look like. Let's just look at that in a little bit more details. Okay, so say it's being processed, so say the particle is being produced through E plus E minus, goes to say a vector bosons, either on shell or off shell, and that vector boson decay into something else. So that's, for example, a typical process at lab. You know, when you have the Z being produced and then Z decay into other things, you can do tons of studies over there. So in general, when we write it down, you will end up with a Bragg-Wigner resonance, which is some pi factors, some spin factors, don't worry too much about it. And then you will have the partial decay width of, oops, V goes to E plus E minus. So that basically taking care of this half of the couplings. Then you have the partial decay width of the V goes to X, which basically taking care of this part of the couplings. And then it's divided by the propagators of the gauge bosons, which is S minus mv squared. So mv is the mass of the gauge bosons plus the decay width of the gauge bosons and the mass. And then you have some other factors over here. Okay, so this is the usual Bragg-Wigner resonance. And it's good in the sense in the time of the lab when they produce tons of Z's over here, the gamma of the Z, the partial decay width, the total decay width of the Z, it's about 2.4 GeV, okay? And the beam spread, which means how well you can measure they can control the beam energies, the delta is about 10 to the minus 3 times the total energies, which is much, much less than the Z decay width over there. So in that time, you can actually vary your S. If you have a control of your center of mass energy, you can really vary your S and measure through the whole line shape. So this is, you can basically mapping out the whole line shape of this cross sections over here when you measure S. So of course you'll get a peak when it's really at MZ, but say if you can, you know, change your center of mass energies at different point over here, you can really mapping it out. Okay, and the width that it's corresponding to over here would give you a good measurement of the width of the Z's. Okay, so the width of the Z would depend on, you know, what are the particles that they decay into, all the particles, electrons, neutrinos, quarks, and all those things. And a precise measurement of the width of the Z's is actually help us to establish that we really only have 3 active neutrinos over here by looking at the precise measurement of the Z decay width. Okay, so that was kind of, and you can do all those other precision measurements at the lab, and that was what they did, which successfully established the standard models. Okay, so that's kind of one case where you have gamma V, which is not so small. And in the case where your gamma V is small, okay, and then you can actually use something called narrow width approximation, which you probably already seen in certain point, which is that the one in the denominator, S minus mv square plus gamma V square mv square. So when the gamma V is really say tiny compared to, you know, the mass of the particles over here, this can be approximated by a delta functions, gamma V mv delta of S minus mv square. Okay, so in that sense, the cross section above the sigma E plus E minus goes to B conjugate, goes to X, not really would proportional to that part is the same, E plus E minus, and then the second part basically become the branching ratios of the V goes to X and the times other things over here. Okay, so that's usually happens in those on-shell productions when I really put my center of mass energy exactly on the mass of the gauge bosons. Then you basically, you produce those guys on-shell and then they decay into whatever the final state you have. You simply just multiply the branching ratios over here. Okay, so this kind of S channel resonance production is actually one of the most important production mechanism for new physics at, say the E plus E minus colliders over here. You really, E plus E minus just the resonance to produce new particles. Okay, but unfortunately for the Higgs, that doesn't happen because E plus E minus goes to Higgs. The Yukawa coupling is tiny. Okay, so that's actually one of the motivations that for those people looking for muon colliders, that you could have, mu plus, mu minus, and then goes to the Higgs, because even though the Yukawa coupling is still tiny, but it's much bigger. It's 200 times bigger than the E plus E minus. Then you can really have onshore production of the Higgs, and then that's why some people were thinking of having muon colliders also at the Higgs factory as well, even though it has its own challenges over here. Okay, but nevertheless, the resonance S-channel resonance production is one of the important production method for the new particles at lepton colliders. Okay, so let's see how the typical cross sections for a lepton collider machines over there. Let's see which one. Get out. Let's see. This one over here. Oops, so to choose. Not this one. Ah, shoot. Okay, let me do it again. I just don't want the E plus E minus one over here. So you guys have certain ideas of, how large the cross section is. Okay. So x-axis is the center of mass energy. Y-axis is a cross section over here. Okay. So the most obvious one that you are going to see is this high peak over here. Okay. So this guy is really the Z resonance peak, because that's when a onshore Z is being produced. So that's why you have this high peak. That's the one that we just mentioned. But other than this peak, you will see the cross sections for most of them kind of go down. Okay, so that's typical for S-channel process, or for the process that has a finite scattering angle over there. The cross section goes as 1 over S. So the center mass energy goes up, then it goes down a little bit. Okay, the exceptions is actually those T-channel processes that I mentioned earlier, because for those T-channel processes, you have, especially in the forward-backward directions, you have those collinear scatterings over there. Then the cross sections actually goes as log of S and modulated by whatever the particle mass that you would have over there. So the cross section actually not going down, it's actually going up a little bit. And one good example is actually, let me circle this one out. This guy over here. So the process we're looking at is E plus goes to mu, E minus goes to mu, and then you have a W, then W, then you have a Higgs coming out of it. Okay, so this one actually carry a special name. It's called the weak boson fusion processes, because the Higgs is really coming out of the two weak gauge bosons over here. So when you look at the corresponding cross-section curve, I mean, it's small, but the Higgs production at lepton colliders was small anyway. So that's this lines over here. Okay, so you can see that the cross-section actually goes up a little bit when the center of mass energy goes up. But at low energies, it's this one over here, E plus E minus goes to ZH. And if I draw it, it will be E plus E minus goes to a Z, then a Z, and H. So this is actually the dominant projections for the Higgs at a low energy lepton collider. So for example, all the Higgs factory that we were talking about mostly making use when they looking at square root of S somewhere around 250, 240 GeVs, this is a process you're looking at. So they peak around 240 to 50 GeVs, then it goes down. But the other process kind of goes up. This T-channel process kind of goes up. So when you look at the low energy E plus E minus, it's a ZH that will be mostly produced. And when you look at the high energy, for example, ILC or click, then it's those weak boson fusion processes will be produced over here. Okay, so the basic idea is if you have S channel, the cross section goes like 1 over S. But if you have a T channel, the cross section goes up kind of like log of S over there, and they kind of trade off at a certain point. Okay, so that was like the typical processes at Lepton Colliders. Any questions about Lepton Colliders? Because otherwise we're going to move on to the next machine. Good. Okay. Nothing on chat, right? Just to check. Okay, I think I'm clean. Okay, so the next things is actually the ones you have been heard about quite a lot, because this is a machine that we have right now, the Hadron Colliders, the LHC, okay? For the past, 10 and the next 10 years, it's a Hadron Collider world over here. So you better know something about the hadrons, even though I haven't really talked about that so far in my lectures. Okay, so most of the hadron machine we talk about, let me just use protons, okay? So proton, antiproton, that was for the Tevatron at Fermilab, or proton-proton, that was for the LHCs over here. So when we talk about a proton, okay, that's our cherry pie over here. And you have your partons, those are the valence quarks, or the C quarks. Then they're connected by all those gluons over here. Okay, so you would have the partons as quark, you have tons of quark. Then you would have the gluons. And other than that, you also have, for the quarks, you have those valence quark. Okay, U and D's that you have. And then you also have those C quarks. Those anti-U bar and D bars and SS bar, CC bar, BB bar, basically those kind of stuff. Okay, so when they collide with each other, so the two proton beams are still symmetric. Okay, they're accelerated to exactly the same the same beam energy over there, and then they collide. But when they collide, what actually happened? Let me see. Let me just borrow one of the pictures over here. So you will see there are lots of things coming out of it, but most of the things are the ones you don't want. Okay, so those are given, you would have initial state radiation, final state radiation. I guess Laura probably talk about that, because I see in the Slack channel when students are asking about the final state radiation of the gluons and stuff. So good, that saved my time. Okay, you will, but those for us, I mean, if we really want to study the hot cross scattering over here, those are kind of the thing that we do not want, okay? As well as those black arrows, so the so-called underlying events, those are just the other non-interacting partons, just the remnants that goes through each other. And so those are not the one we want. The one we really want are those hard processes or hard scattering, the one which is indicated by the red arrow, sorry. The one that's indicated by the red arrows over here, those are the high energy collisions. Okay, but on the other hand, lots of your detector, most part of it detector will be fired up by those unwanted stuff. Okay, those good things are really rare over here. So one of the main things in the hadron machine, it's really challenging, is how to dig out those rare good events out of, those a bunch of uninteresting but underlying stuff that's there. Okay, so let me give you some examples of just like the hadron the Lepton machines we have. We also have a list of hadron machines. Let me see the others. Which one it is? Probably this one over here. Let me see, I got it. Oops, sorry. What's the other one? Okay, so those are the, again, the one on the top are the hadron machines that we have or had before Tevatron. Hera is actually a EP collider. I think that should probably be 0 point. I don't think they got 3.14 TeV. That would be really nice. Okay, and the LHC is the current one that we have right now. Okay, so the Tevatron is a PP bar machines and LHC is a PP machine, because when you get to higher send-off mass energies, the difference between proton and antiproton is really not that big if you consider most of the interesting physics processes over there. And the proton is much easier to get high luminosity than the antiprotons. Okay, so for those of you that are my age, you'll probably remember the time when the Tevatron run 2 tons up. I think for a year or two, they really have difficulty to get the antiproton luminosity up. and like oh, we can get to the design center of the luminosities, and it's because antiprotons, and it's very hard to accumulate those antiproton, the luminosities. Okay, but the LHC is a proton-proton machine, so you don't have to worry about that one. So the one we have in the future, people are thinking of, one is a hydrogen LHC, so it's using the LHC rings, but just to bump up the luminosities. And then after that, it's the FCC-HH or SPPC. So this one is actually, as you can see the name, it's connected to the FCC-EE or the CEPC over there, because the idea is actually very similar to the lab and the LHC idea. You use the same tunnel, you put the E plus E minus machine first. After it's done with whatever precision measurements, you take out the tunnel, put back a proton-proton beam. But it's the same tunnel, so at least they save on, you know, the tunnel. And so the same idea over here, you build these rings to put a Higgs factory first and then take it out, then really put in proton-proton beams, and you hopefully will be able to get 100 TeV center mass energy. So that will really become our energy frontier over here. Okay, some basic facts about the hadron machine over here, because it's a hadron machine. As I said, a lot of things will be junk. So the total hadronic cross-section, those actually you cannot get that through perturbative calculations, because those, a lot of them are the low energy stuff where the QCD become non-perturbative over here. But people really have a good estimation using the so it's roughly equals to pi times divided by m pi square, kind of like a good estimations, which is roughly to the order of 120 megabar. So that's a big unit, because if you think about what's happening at the E plus E minus machines, which is mostly electroweak interactions or electromagnetic interactions, it's in the peak bond levels. And for the total hadronic in the PP machines, you're starting from, you know, 10 to the minus 3 bond. That's a really huge, that's really a huge cross sections over here, as you will see in a minute when I actually show you the cross sections. Okay. And then for the actually interesting hard scattering processes that we have, okay, let me write this down first and then I'll explain. Most of you probably seen that already, hopefully. So the calculations actually would involve a convolution of the parton level, because as I said, the actual process is a parton level. Parton A and B goes to a particular final state, okay? But it will be convoluted into something called the parton distribution function. So let me write it down for the moment. I'm going to explain in more detail later, okay? So PA and PB, those are the so-called PDF, not the usual PDF file. Parton distribution functions. Okay, that basically tells you within a proton how much probability is chances you're going to find a particular parton at a certain energy and the momentum transfer over there. Okay, so I'll talk more about that later, but for the moment, let me just list this as that's how you get the cross sections. You convolute, so this sigma hat is the parton level cross sections, which you can basically calculate using your perturbative calculations. And then you convolute it into the PDF, sum over all the possible partons that you're contributing, you get the total cross sections. Okay, so I'll come back to, I promise I'll come back to the PDF later, but for the moment, let me just tell you a couple of the kinematics, and also, yes, we need to go through this. Let's see, what's the advantage? Same as the leptons. What's the advantage and the disadvantages of the proton-proton machines? First thing first, whatever the lepton collider is missing, hadron collider is good at, is that it has very high center of mass energies. As you can see, people even thinking about 100 TeV machines over there. Okay, so let's work out the numbers in a little bit more details. So that's proton with the partons inside, then they collide. Okay, sorry, there should be the same arrow over here. Okay, and as I said last time, the kinematics we set it up, P1 is E0, 0, E, and the P2 is E0, 0, minus E. So they are very good, you know, symmetric beams over there. Okay, so the total center of mass energies is 4E squared. So that part is identical to what we had before. Okay, But on the other hand, the actual parton momentum that's carrying P1, little p1, is x1 times capital P1. I'm sorry, I should call this capital P1. Okay, and that's capital P2. And the little p2 is x2 times capital P2. So the x1 and the x2 are two new variables I introduced, basically tell you how much fractions of the parton momentum is in terms of the original proton momentums. So if I calculate S hat, which is the parton send-off mass energies, which is little p1 plus little p2 square over here. Okay, so that will be the send-off mass energies of the parton square. Okay, so it will be x1 plus x2 square minus x1 minus x2 square. Okay, so you end with e squared. So you can see unless you happen to be x1 is exactly equals to x2, okay, then your parton send-off mass frame is the same as the left frame. But most of the time you're not going to be that lucky over here. Okay, the x1 is not equals to x2, so that's actually equals to x1 times x2 times s. Okay, so the actual interacting send-off mass energies is going to be much smaller than the original machine send-off mass energy over there. Okay, if I take some typical numbers, and x1, as we'll see in the parton distribution function later on, it's somewhere about 0.3. And x2, it will peak somewhere about 0.3 over here. So if you put these two numbers together, you can pretty much approach new physics mass scales about 0.3 of whatever send-off mass energy of your machine is. Okay, so say LHC is 14 TeV over here, you're basically looking at effective send-off mass energy of about 40 eV. Okay, so that's why when, for example, when you look at the SUSY Greeno searches and things like that, they can, really cover Greenos up to a few TeV regions. You're never going to get to 13 or 14 TeV because, it's the parton inside the protons that's been interacting over here. Okay, so this S hat is a good thing to keep in mind whenever you're talking about the hydrogen machines. Okay, even though they can reach higher send-off mass energy, but the effective ones will be a little bit lower. But even though it's a little bit lower, it's still better than the E plus E minus machines, generically speaking. Okay, and the second advantage, high luminosity. As I said, once you go to higher send-off mass energy, the different higher momentum, the difference between proton and antiproton is not really that big. Okay, so unlike the E plus E minus machine, you pretty much have to use E plus and E minus to be able to access something interesting. Here, I don't have to have anti-proton beam. I'm perfectly fine just with a proton beam over here. So it's relatively easier for us to reach higher luminosity over here. So for example, LHC luminosity is about 10 to the 34 inverse centimeter square inverse second, which translates, we did this yesterday, 100 inverse Fak bond per year. Okay, and if you think about the typical cross sections for the W production, TT bar production, the blah blah blah, you would have 10 billions Ws, and you would have 100 millions TT bars over here. So it's LHC is really a top quark factory, going to produce 100 million of them. Then even though it's a messy environment, you can still dig them out. You can do all the nice measurements for the top quarks and determine its properties. So sometimes people also call LHC a top factories because you can really produce a ton of them. And even when you look at the amount of Higgs that's being produced, you actually also reach 1 million. Okay, for those of you who still remember when I talk about Higgs factories, CEP, CRF, CCEE, they also produce about 1 million. So LHC can actually produce about the same amount of Higgs, standard model like Higgs over there. And then your question is, okay, it's also a Higgs factory, why bother to build another one? Okay, remember that's 1 million Higgs over tons of backgrounds in a very messy environment. You're not going to catch all those 1 million Higgs over there. Unlike in the Higgs factory, in the Lepton machines, 1 million produced, you can probably catch almost every single one of them. Okay, so even though we do produce a lot of Higgs, a lot of them is unfortunately not, you're not going to find them. Okay, another thing about proton-proton machines, it's a proton, right? So it has a strong interactions. And the reason it's called strong, it's strong. I mean, it's more interactions than electroweak or electromagnetic interactions. So you would have bigger cross sections, especially for the final state object that carries standard model color. Okay, so in terms of, the electroweak particles, you don't really have too much advantage over E plus E minus, except you can reach higher mass. But for strong interacting particles, you do, because they go through strong interactions, you have much bigger cross sections, so you can produce some, and also you have higher center of mass energy over there. So that's a good thing.
I'm not sure.
Yes.
Sorry, I'm not sure if this is the right place in the flow to interject it, but there's a question about a factorization scale in the chat.
Okay. So I will just say wait until I talk about the PDF. Yeah, so I'm going to talk about PDFs later on. So for the moment, let me just go through the advantage and disadvantage. Okay, so once I'm good there, I'll come back to the factorization scales. Okay. And if I don't have it, just remind me again. Okay. Yeah. So okay. And so that's, yeah. So we have strong inter, so good. You have bigger cross sections. Oh yes. Another thing is E plus E minus. As I said, you only have E plus E minus. Okay. So you're good to produce kind of spin 1 particles. You're not really so good for the spin 0 and the spin 2 over here. Here, because it's proton-proton, proton has quark and gluons. So you have tons of initial state to play with. I can have QQ bar. I can have Q and the gluon. I can even have gluon and the gluons. All those different combinations over here. And I can also have, quark goes to quark, quark goes to quark. I can have those T-channel processes with weak boson fusions and all those sort of stuff over here. So I can have W and W, Z and Z, W and Z's, and all those different combinations. They can even have same signs, no problem with that. Okay, so I would have access to a bunch of final states with different charge, with different spins, and all those sort of stuff. So I will have access to a big varieties of new particle state over here. So that was the advantage of a proton machines. And of course, it always comes with disadvantage, and some of them I already mentioned. Sorry, I can't spell now. Okay, and the one is, you probably already guessed the second one, but let me do the first one first, is that the initial state is unknown. In the sense that I'm really picking out a pattern out of the protons with momentum x1 and p1, okay? So that we can do that after we integrate out all the possible range of x1, but for a particular process, event by event, we don't really know what x1 is. Okay, so in that sense, the initial state kinematics is unknown. Unlike E plus E minus collider, I know exactly what the momentum of my E plus E minus is. Here, for the proton-proton machine, I don't. Okay, so the most I can get is S hat is Sx1 times x2 goes to S, but again, I don't really know event by event basis what is, what is my x1 and what is my x2 is. So in the Z direction, I can't use the energy momentum conservation in the Z direction. Because I don't know what the initial momentum in the Z direction is by the partons over here. You can, however, still use energy momentum conservation in the transverse plane. So that's why in hadron colliders, we talk about transverse momentum and things like that. Because for the transverse plane, it's to a good approximation, the total initial momentum is 0. But for the longitudinal, for the Z direction, we don't really know over here. So we need to rely on the final state momentum measurement to get the kinematics. You just cannot use the total PC because we don't know what's the initial PC that you have over here. Okay, the second disadvantage, again, you have a large rate. It comes as either advantage or disadvantage. Advantage, the large rate for the signal projections. Disadvantage, the background also have large rate over there. Okay, so you have basically a very hostile environment. And actually it goes even worse than that. Okay, it's not only your background that gets huge, you even have trouble to recording all the events because the event rate is just too big over there. So I'll come back to that later when we start talking about the triggers. Okay, so now to do any analysis in the Hadron Colliders, let me just talk a little bit more about kinematics because there's something special about the hadrons about hadron machines that we usually use. Okay, so I just want to introduce the language. So next time when you see it, you know what people are talking about. Okay, so the same picture, pattern in a proton. So let me just do what I did earlier. X1, P1, X2, P2 over here. Okay, and so the thing you usually hear people talk about is rapidity. Okay, it's defined. It's basically you can use. It's defined in a way it relates to the energy and the z momentum. So it's defined as 1/2 log of E plus Pz over E minus Pz, where z is it's a z direction momentum. So for any final state, you can measure the Pz, so you can know what the rapidity of the final state guy is. Okay, so usually you will characterize, a momentum by the energy and then the theta and the phi and all those sort of stuff. You can actually write down a full momentum completely using the rapidity to use that to replace the polar angle theta over here. So it'll be, so let me write it down because we might need to use that later, or you'll see it somewhere. Posher of y, pt cosine of phi, pt sine of phi. So those are the px and py. Then you have the et of sinh of y. Okay, where the et is equals to square root of pt squared plus m squared. Okay, so sometimes you will see people use the rapidity and then the et and the angle phi to describe a particles instead of the usual theta. So what's the advantage to using this rapidity over here? It's because we know we are in a boosted system. The center mass frame is not the same as the lab frame over here. So the polar angle theta is of course not boost invariant. It is not boost invariant. Okay, but under the boost, let's see how the y change. So the y prime under the boost, it's 1/2 of the log of e prime plus pz prime, e prime minus pz prime. So that's just definition. But let's boost it back. Let's boost it back to the original ones. It will be 1/2 log 1 minus beta center of mass, which is the center of mass frame over here. And then the original E plus PZ, E minus PZ over here. Okay, so this guy over here is actually the rapidity of your parton center of mass frame. Okay, so Y of the center of mass frame of the partons is, let me see. It's actually relates to 1/2 log x1 over x2. You can easily work it out because you can work out the beta of the center of mass frame over here. Okay, so once we have that, the rapidity after the boost is y minus y center of mass of the original parton that you start with over here. Okay, because that will be the same for all the for all the things that you have over here, then d over dy is basically d over dy prime. Okay, so that's advantage of using the rapidity instead of using the angle theta over here, because it's basically boost invariant. Okay, unlike the polar angle theta, it's not, the formula will be far more complicated when you look at how the angle theta got changed after you do the boost over there. Okay, so that's why you will see that in the Hadron Colliders, people actually use the rapidity quite a lot instead of using the polar angle theta over here. Okay, and another usual one you will hear people say is something called pseudo rapidity, eta. So that's basically in the massless limit. So in the massless limit, most of the jets and the electrons and the muons, they are light enough, so it's very easy to do it for a massless limit. The y basically goes to 1/2 log 1 plus cosine theta over 1 minus cosine theta, which is log of cotangent theta over 2. That's what people define as eta. So that's what when you look at, you know, the experimental papers or, you know, the Delphis or the PGS, and you will usually hear people talk about eta. That's exactly what that eta is. That's what the pseudo rapidity is. Okay. So instead of using E and the theta and the phi to characterize the momentum for particular particles, you can simply just use PT, eta, and the phi over here. So you will never hear people talking about what's the polar angle theta. Instead, you will hear people talking about what's the pseudo rapidity over here. Okay, so in the 90 degrees, eta is equals to 0. In the plus, yes. And then in the forward and backward directions, eta is pretty much infinities over here. Okay, and another thing you would see in the hadron colliders when people present the experimental results is you will see such kind of, yes, here it is. You will see such kind of a so-called Lego plots. Okay, and you can see where it is. So one axis is eta, it's exactly the pseudo rapidity, and then the other axis is the phi, which is the mutual angle over here, and then you will see how the ET is being distributed. Okay, so that's exactly the reason people use eta and the phi instead of theta, and the phi is over here. And another useful thing that you usually hear people talk about when they in the hadron machines is something, oh, it's in the Lepton machines also, delta R, the separation between two objects. Okay, it's defined as delta eta square plus delta phi square. Okay, it's actually a very nicely defined object because it's invariant under the longitudinal boost if you boost in the parton center of mass frame. Okay, because delta eta, as I just said, all it does is shift a overall YCM, so which is the same for everything. Okay, and the delta phi, it's defined in the transverse plane. So again, it's boost invariant. So the definition of this delta R is actually nicely, it's actually nicely invariant object over here. Okay, so you will see that, you know, in the jet definitions of, you know, a jet within a certain radius of delta R over there, or you're talking about the separation of two objects, what's a delta R between those two, so that's what the delta R is. Okay, so that's another good thing in terms of the kinematic variables people discussed when they talk about hadron colliders. Okay, so let me see if there are question coming up. Let me see. Okay, that goes to with the rapidity and pseudo rapidity. Yeah, if you look at my lecture notes, you'll have a little bit more details about the derivation over here. You can also do this as an exercise by yourself, okay, to work out the kinematics. It's actually useful. Okay, so now back to the things I promised I was talking about, parton distribution functions and the factorization. Because this is also an important subject for hadron machines compared to the Lepton machines. In the Lepton machines, we almost never need to worry about that unless you're talking about, you know, a virtual photon coming out or something like that. Okay, so let me keep doing this over and over again. Okay, so you have this X1 P1, and then you have this guy as X2 P2. Okay, so what are those FA of X? Or sometimes people have Q square also. Okay, so those are so-called parton distribution functions. So what that is the probability of finding a particular parton A inside proton, okay, for a momentum fraction X at momentum transfer Q squared, okay? And so the thing is this FA, so this FA, unfortunately, you cannot calculate them. Okay, so because it's really to do with the low energy physics where everything gets non-perturbative over here. So cannot be computed, okay? But on the other hand, we can still use them because they can be FAs of X. They can be measured in the sense that we can measure certain things. Then from that, we do the data analysis and fit into the data, and then we can infer the values of the FA out of it. Okay, so there's a couple of groups in the world who does that. And one is the CTEC group in the US. And then I think the other one, I might get the name wrong, MIST or something like that. Okay, so there are a couple of groups of CTEC. So when you do the detectors, when you do the collider analysis, you will see people ask you to choose which set of PDF that you want to use, a different set of PDFs. So that was referring to those FA of X that is. Okay, and another nice thing about this FA of X is that they are universal. Okay, you can measure them at one experiment and use that in the other experiments because protons are the same protons over there. Okay, so it's actually universal functions. As long as the kinematic region can be applicable, you can basically use the FAX in the, once you actually measure them and extract them, you can actually use it everywhere over there. Okay. And now come to the factorizations. I wrote down this cross-section before. It's a cross-section of sum of A and B's, dx1, dx2, and then let me ignore the q square, FA and the FB of x1 and the sigma hat over here. And that is so-called factorization for obvious reasons, because you can see I factor out the short distance in the short distance process, which is where the pattern cross section is, with the long distance effect, where is those PDF is. Okay, so intuitively, at least it makes sense, right? Because short distance hard scattering processes is just whatever it is. In principle, you can separate it nicely with the long distance effects, which are those PDF is. Okay, in practice, I mean, we are serious. So we always want to prove things, right? In practice, unfortunately, this factorizations is very difficult to prove that it is actually true. Okay, even though we all believe that it's true, you just can't prove it from the first principle over there. Okay, but however, even though we can believe it, but just to be, even though we cannot prove it, but just because intuitively it's so nice, right? So however, people can, we can still use them. Okay, so you can still safely just use it, and it also works out very well. Okay, in practice, we can just use the PDFs of FA and use these factorizations and get the prediction of the overall cross sections, compare with experiments, and the things actually fits very well. Okay, so this factorization, in some sense, it's like a conjecture, but it works. It works. Okay, so we actually use this quite a lot in the Hadron Colliders. And let me see. So how does the PDF actually looks like? Let me actually, and then I'll come back to that factorization questions that was asked earlier and see if I can possibly answer them. Okay, so this is how those PDFs look like. The x-axis is X, and the y-axis, you more or less, you can take that as my FA over there. Okay, a few things, and they are at different scales of the, so the Q square kind of, oops. Okay, I kind of didn't really mention the Q square quite a lot. The Q square is a momentum transfer for a particular process. Okay, so you can see this pattern distribution functions, actually it varies with the Q square over here at low momentum transfer Q square versus high momentum transfer Q square. They actually look somewhat different over here. Okay, so let's just look at one of them and then see what's the generic feature it is. And then I'll come back to that factorization question that we had over here. Okay, the very first thing you will notice is that for the valence quarks, they have a peak. Okay, so it's peaked around somewhere about 0.3, 0.4 over here. Okay, so that's what my previous estimation of the parton send-off mass energies, and roughly how that is, I use a value 0.3. That's where the value 0.3 come from. It's where it peaked over here. Okay, so when we're talking about the production near the energy threshold, means when we talk about the production of the heavy particles, then usually it's a valence quark. They would contribute because their PDF really peaked towards the higher X over here, okay? But on the other hand, when you look at the gluons or the C quarks over here, at low Q square, their contribution is less, but if you compare the left part and the right part, where the right part has a higher momentum transfer Q square over here, you will see the C quark and the gluon contributions actually gets bigger. Okay, so which means when we look at the production near for high momentum transfer, then it's the gluon or the C quark would actually contribute. Okay, so those are derived from this PDF over here. And I believe this Q square is, let me go back to, oops, what do I do? Accidentally stopped share. Yes, yeah, I accidentally stopped. I meant to look at the chat. Okay. Factorization in the context. Okay, what was the original factorization questions? Asked, do we set the factorization scale in the formula, or do we need to worry about the uncertainty from the different choice of factorization scale and even from the choice of the okay, so the question is about the uncertainties introduced by the factorization scales or other uncertainties of the PDF over here when we do, say the theoretical calculations. Okay, I would say unless you're really a QCD expert and want to explore the uncertainties associated with different choice of the factorization scales and all those sort of things, then yes, you do need to take that into account. But on the other hand, for majority of us who are beyond the standard model phenomenologists who is not really QCD expert, I would say don't really worry too much about it. Okay, after all, we're just doing the theoretical calculations, give a predictions of what kind of new physics you can see, and the number whatever the reach number you get out, it's always have certain uncertainty. We know that experimentalists won't take it literally as it is anyway, so it's just to give them a order of magnitude kind of sense of whether this particle can be reached with that energies or with a particular process or something like that. So I would say most of the time you don't really need to worry about the uncertainty caused by the choice of different factorization scales. How the cross-section will vary by choosing different factorization scale. I would say most of the time don't really worry too much about. But on the other hand, if your specialty is QCD, then you do. Okay. Okay, I think the time is almost up. I have a little bit of the hydron things, but actually, can I have 5 more minutes? Because I want to kind of just finish what we have for the hydron cross sections, so that
sure, why not? Go for it.
Okay. And we start late. Let me get myself excused. Okay, so just like I showed you a E plus E minus cross sections, and typically what's the size of it, and let me also show you what's the typical size for the hydron cross sections at hydron colliders. Okay, so this x-axis again, it's center mass energy, and the y-axis is the hydron collider cross sections over here. Let me just pull out a couple of highlights. So first thing first, this is the total hydronic cross section that I'll talk about earlier. It's way up over there. That's going to set the background for everything. Okay. And then everything else with the curve over here are basically different interesting processes of what the cross section is. And you can see it's already, compared to the total cross section, it's already 5 or 6 order magnitude lower over here. Okay, even say for the total jet projection cross sections or the BB bar cross sections, which are probably the bigger ones, it's already, you know, several order of magnitude than the total cross sections. And then you might wondering why one of them goes down, the blue lines kind of goes down and this BB bar kind of goes up. It's because of the different cuts. You have to put certain cuts because of the singularities that you have over there. So you have to put certain PT cuts. The one with the total jets, the PT cut is actually related to the center mass energy over here. So, but for the one for the BB bar, it's a fixed. So when the center mass energy goes up, your cut doesn't really get stronger. So the cross section goes up. But for the total jets, it actually goes down because my cuts actually gets stronger over here. Okay, and then a couple of interesting process. This is a TT bar that I was talking about. LHC is going to be a TT bar factory. One of the green line, this guy over here, is the dominant projections for the Higgs projection. So that's gluon fusions with the triangle diagrams of the Higgs. Okay, even though this is a loop processes over here, but because Higgs only have electroweak interactions, okay, and it's not even charged. So this one, even though it's loop induced, but because of the gluon, you have so many gluons in the protons over there. That's why this is actually the dominant projection cross sections at hadron colliders. And the one followed by that is a weak boson fusion process. It's the one which I just draw. So you radiate out two weak boson fusions with a Higgs over there, okay? And that process could become important as well. Okay, so I think I'll probably just end up with this part today, and I actually don't have time to talk about detectors, so I think that for the next lecture, which is the last lecture, the first half will be about the detectors and how we're looking for things at detectors and also the trigger. And the second half will be about some typical kinematic variables that we use to do the kinematic, to do the collider analysis. Okay, so that will be for tomorrow. Any questions? Let me see. The question on the last point of the advantage of a bunch of finite state wouldn't be the same. Can it be a little bit more specific? What do you mean we have a bunch of final states, huge background noise?
I think she means that you can produce everything with enormous cross sections, and so
yes.
background.
Yeah, it is. That's why this sigma total is big. But for each, so that actually goes to the next lectures is how we make use of those kinematic features to do cuts. So far, I have not talked about cuts yet, but lots of the collider analysis is actually to do with cuts. It's not just about produce some. Once you produce some, you actually need to distinguish between signal and background and actually pick out the background, and that's how you distinguish from the different backgrounds. Yeah, so that's also why when we, so for example, the Higgs over here, let me give a particular example. The dominant branching ratio will be H goes to BB bar, 60%. And if you think about the Higgs discovery processes, when it's first coming out, it's H goes to gamma gamma. It's a loop processes. The branching ratio is probably about, if I'm not wrong, 10 to the minus 3 or 10 to the minus 4 over there. It's tiny compared to the BB bar. But it's actually good because the background for H goes to gamma gamma, it's also small. I mean, there's almost no standard model processor will give you gamma gamma. And then the only one probably coming from, you know, the detector backgrounds over there. So it's a small signals, but you have even smaller background. Unlike H goes to BB over here, you have this huge sigma total, or even this guy here you need to worry about. Okay, so it's always a comparison between the signal and background, and I'll talk a little bit about that in next class, about how to pick out signals out of the background. Any other questions? Nothing? Good.
Any other questions?
And again, I will send my lecture notes to Ethan, and he can upload it. You should already be able to find the yes to his lecture notes online already. Okay, the actual lecture notes, I put a bit more details compared to what I talked about in class. Okay.
Okay, great. I don't see any other questions popping up. Wonderful. Well,
well, I'll see you guys
end of the day. So see you tomorrow. I guess
so tomorrow will be the morning time, right? I switched with Adam.
Right. Yes.
Okay.
Yes.
Sounds
All right,
good.
take care. Have a good evening.
Mm-hmm.
Bye.
Bye.